Okay, so picking up from where we left off last time, we were talking about triple integrals, and in particular, worrying about how to turn triple integrals into triple iterated integrals, which involves this kind of slicing up process, which is heavily geometric. Right. So two more examples I want to show you, and then we're going to move on to the next section. What's interesting about this next example is how to draw it. It's largely sort of an artistic study here. This is on its face, seemingly a really, really hard problem in that we have 5 planes, and we've got to figure out how do these 5 planes bound some solid. And oh my gosh, right? I mean, this is potentially really, really difficult. In general, if these were arbitrary planes, this would be, in fact, very difficult, right? But this is not exactly what we're facing. We have 5 planes, of which some of them are extremely convenient. And the point of view I want to take on this is to notice that 3 of them, in particular, have no y's in their equations. And flash back to chapter 1, when you have no y's in the equation for a plane, that means that those planes are all parallel to the y-axis. So I can actually draw those planes pretty easily. What I'm going to do is I'm just going to look inside of the xz plane. I'm going to draw what their intersections look like in the xz plane. They're just lines, right? And z equals 0 is like that. And let's see here. Z equals x would be something like that. And let's see, x plus z equals 2 would be something kind of like that, right? And altogether, I can already kind of see what's going on inside of here. Really, it's this triangle that I actually care about. That's what has sort of an inside, if you will. And so now, keeping in mind that what I actually want is the planes, I'm then going to take this triangle and kind of drag parallel to the y-axis, kind of like that. And so this is the prism that you get when you look at just those 3 planes. And now that we're 3 down, 2 to go, right? We can just kind of take them one at a time with what's left over. So let's start with y equals 0. Yeah, no sweat. That's the xz plane. That's going to intersect this prism on that face. And then we'll look at this last one. This is the weird one. And okay, it's we've got this is something kind of like that, right? X plus y plus z equals 3 is going to kind of cut through at an angle. And you just have to kind of think geometrically about that, but then that intersects in this face right there. So there you go. So this is what this solid looks like that's bounded by these 5 equations. Everybody see how that, in this particular case, taking advantage of the conveniences that we have here, we're actually able to make this drawing. Everybody all right? I'm going to be on the lookout for this. This is a very convenient thing to have a bunch of planes that you can just instantly take advantage of. Yeah.
Sorry, could you do x plus z equals 2 again?
Yeah, so thinking about x plus z equals 2, this one right here. And I was thinking first, just inside of the xz plane, this intersects the x-axis at 2 and the z-axis at 2. And so it's kind of this line, but of course we're only interested in how that pertains to how it intersects with the other lines, and so I actually only need just this part here. Yeah, no worries. Okay. All right, so now with this drawn, let's take this as a slicing and dicing problem. Now, I do think this is a healthy exercise to think through all of the different 6 ways that you can slice this up. And I claim that as you slice, you're going to hit corners in most of the different approaches that you could take to slicing up this solid. For example, if I were to put dy on the outside, here's what some y slices look like, etc., etc. And then you can see from the picture I'm going to hit that corner, after which the slices are going to look significantly different. At which point I'm going to hit this corner. after which time these slices are going to look significantly different. Like that. Right? So putting dy on the outside would be catastrophically bad. So try the other several different ways of doing it, and what you're going to find, and again, healthy exercise. It's an exercise in geometric thinking. It's an exercise in geometric drawing, which again, really important, really unavoidably valuable in these kinds of questions. And what you're going to find is that this is the only one that actually works well. Now, that's a not immediately obvious conclusion. Let me show you what I think is a better way to think about it, and that's this projection point of view. Y'all recall I'm a big fan. Right? If there is a good projection, keep in mind, good projection, that comes with a few requirements. If there's a good projection, that motivates what you should do. So I make the observation that projecting into the XZ plane is actually really good, because we have a triangle as its cross section. That triangle is going to be pretty easy to slice up. No problem. The lower bound, for y, from a given x, from a given z, as y ranges, the lower bound is always going to come, well, from that same plane, which of course is where y is equal to 0. And this upper bound, this point, the upper bound, is always going to be on that surface in which you can solve for y, and y will equal to that. It's just a matter of looking at what the equation of that plane is and literally solving for y. And so, boom, very convenient, right? Not that much trouble. We didn't have to do a whole bunch of three-dimensional drawing, and we're able to get to a good slicing order and get all of our bounds. Yeah.
Wouldn't there be a corner if you integrate up, like across the triangle?
Well, it depends on how you slice it, though, doesn't it? So let's worry about that for just a second. I'm going to get rid of all the mess here, and again, I claim in the XZ plane we have this, right? But notice I am not slicing with dx on the outside. If I were doing it like this with dx on the outside, then you're right. I'd be, my x slices would look like this, and I would hit that corner. But very importantly, I'm not, right? And I am, in fact, doing dz slices. First, my z slices look like this, and I don't hit any corners until the end when I'm done anyway. Yeah, so that's the argument for why specifically I want dz there on the outside. Yeah. Everybody good with that? All right, so again, projections. Very convenient for this kind of a problem. Okay, next example. And this one, oh my God, so convenient to use projections. This is a terrible, terrible example if you don't understand projections. So here we go. We have ourselves a paraboloid, right? Chapter 1 flashbacks, or chapter 2, maybe somewhere along in there. And that's this. And then we have this, also a paraboloid, which something kind of like that. And our region is what is bounded by those. In other words, what's kind of sandwiched in between. But I have to complain about my own drawing here. It's a hard thing to draw because there actually is kind of there's a hollowness inside of there. I've left it white because it's not solid all the way through, but then again, there is kind of some yellow that kind of on the near side of the hollowness, and there's some yellow on the far side. It's a hard thing to draw a good picture of, right? It's really pretty ugly. So how would we slice this up? And just for dramatic purposes, let me take an attempt that's going to be pretty fantastical failure. I'm going to try to draw a slice perpendicular to the z-axis just to see, right? And this is not my first time to take a whack at this, and yet it's still going to be pretty bad. I claim that the cross sections would look something kind of like that, perpendicular to the z-axis. I don't know if you can kind of see what's going on there. But I think what you can see is that that's hard to draw and hard to deal with. So all else being equal, we don't really want to do slicing of this solid. But let's take a projections point of view on this. And in particular, you'll notice pretty quickly that it's nice to solve for y, which means I'd really like to have dy on the inside, which means that if I'm going to do a projection, I want to project into the xz plane. That projection, no problem. Projection is a little disk. Now, a little bit of algebra to think about the details of that disk. It's defined by where these two paraboloids intersect, and so you set the one y equal to the other y, and blah blah blah, and you get the equation of this circle that bounds that disk. A little bit of algebra, but no big deal. Nice projection. And then let's think about the lower and upper bound surfaces, and for a given value of, let's see, I'll do it like this. For a given value of x and z, anywhere in that projection, as I move in the y direction, right, we're going to enter the solid on this paraboloid, and then we're going to proceed for a while, and then we're going to leave the solid, gosh, this is hard to draw, but on this paraboloid. Does that make sense to everybody? Again, it's a hard picture. It's hard to visualize. But the algebra works out great. Let's say, oh, I had a better picture. Oh, look at this. I already had this drawn. I forgot. So let me do this again. So x and z range over these values per the shadow that we just talked about, right? And then we enter the solid on that surface, which gives me this lower bound for y. And then y ranges from that lower bound up to this point on that surface, which gives me that upper bound. Everybody see that? Again, if only from an artistic standpoint, I think much easier to draw. And so this projection point of view, very, very handy. And I hope you'll capitalize on it. I wish the book had spent more time talking about this. Okay, so we're moving on now. I'm going to talk about section 5.5, change of variables. This is a kind of another example of, whoa, what's going on here? My stylus is, okay, there we go. Another example of a general trend you've probably noticed, you're going to certainly notice over time. What I like to do is I take single variable calculus ideas, look at them from a certain point of view, and with just a certain point of view on the single variable calculus idea, it's easier to see how in fact we're just generalizing to a multivariable setting. So what I'm going to generalize here is the substitution rule. Let me go ahead and go full screen here. So the substitution rule, and I'm sure you all remember the substitution rule here. And the big idea is that if x is equal to g of t, then dx is g prime of t dt. That's just kind of an algebraic little shorthand that we like to write. And then you plug that in and bam, right? Very convenient, helps you solve a bunch of integrals. Nice tool. Okay, I want to take a different point of view on that. Rather than thinking of this as kind of an algebraic trick, I want to think of this a little bit more geometrically. I want to think about how this function g that gives me x as g of t, right, is literally taking points on the t-axis that go into this function, and then points on the x-axis are what come out of this function. All right, so I want to think of it, we're going to explicitly think about that domain, and we're going to explicitly think about this target. Yeah? All right. So let's think now about what happens to this little subinterval right here of width dt. You can think of dt here as being a size. That's how big, that's how long this little subinterval is. Now, let me think of that a different way, though. Let's think of dt as representing not a size, but a change, in the sense that I could think of myself as starting here, and then when I move over to the other side of this subinterval, then I'm here. And so I have moved, my t position has changed by an amount dt. All right? So it's an input change. Well, then I can look at the corresponding output change, dx, and I can pretty quickly relate the input change to the output change, because we have one of our basic ideas from chapter 2. The derivative is the relationship between input changes and output changes. So here it is. Dx is going to be the derivative times dt. Specifically then, this g prime is what we multiply by the input change dt to get the corresponding output change dx. All right? Okay. And now, I'm going to revert back to thinking of these as representing sizes. So now forget about changes. We're going to think of dt as representing how big this little subinterval is. I'm going to think of dx as representing how big this subinterval is. And in fact, what's going on here is this function g is taking a little piece of the t-axis that has a size and plugging all those points into g. When they come out on the x-axis, they've been stretched out. They're bigger, right? Their image interval is a little bit bigger, just as I have it drawn here in the picture anyway, a little bit bigger than the input interval. And again, you might say it's been stretched out, and by how much has it been stretched out? Well, you can see that right here in this formula. It's been stretched out by a factor of g prime. Okay. How are we doing? Everybody all right? Okay. All right. Here's the second point of view I want to take on this. This is the idea of a pullback. Now, y'all are accustomed to the idea of a function having a direction, right? And what I mean here by g having a direction is that points come from the t-axis, they go into g, and they come out on the x-axis. Points go that way. And when we say the points go this way, I like to think of this as g is pushing them that way, because they go from over here to over there. Here's the weird thing. Points, yes, they go that direction. But when I plug in, for example, keep in mind x. I know what x is. X is g of t. That's a formula that I have for x. And in the act of plugging that in, where I see x's here, an expression involving x goes the other direction to turn into an expression involving t's, which is strange because the function goes that way. But really, better way to say it, the function pushes points forward and it pulls expressions backwards. That's just what plugging in is. And now notice we can plug in the other thing we've got a formula for. We just got an expression for dx. dx, when you plug that in, again, that part pulls backwards. It goes the opposite direction to the direction the function goes. So this is called a pullback. It comes up in many places in math. This is a nice way of thinking about what's going on here as well. And so with these two observations made, the idea that a substitution on an integral involves pulling back with a stretching factor. And with that, with these two ideas in mind, we're now going to try to do the same thing for double integrals. Let's get our setup going first. We're going to presume that we have some domain over here in the UV plane, whatever, some domain. We're going to imagine plugging into this function what we're going to call a change of variables function. This is analogous to the substitution function. And each one of these input points, I plug into this function, and what comes out are a bunch of output points that will create some sort of a shape here, like that. And we're going to start in the same place we did above, which is to imagine that we're interested in doing an integral on that output domain. Maybe I want to compute the mass of this thing, or maybe this is a weird swimming pool I have in my backyard, and I want to compute the amount of water it would take to fill that swimming pool, which is a surprisingly large amount. And I want to figure out how to pull back. I want to take everything that's on the right in terms of x's and y's and rewrite it in terms of u's and v's. Fingers crossed, hopefully, to make it into an easier integral. Okay. All right. Is everybody good so far? Okay. Keeping in mind that when we say that this function g goes from the UV plane to the xy plane, what that means is xy is g of UV, which means that this xy right here, I can plug in literally exactly what it is. It is g of UV, and again, that takes my expression that was in terms of the right variables, and it rewrites it in terms of the left variables. Now, the tricky bit is, what do I do with these little bits of area? Let's see here. This area, let's see, let me do it like this. This little area right here, dA, how much area is that? In particular, how does that relate to this little piece of area? How, du dv? What's the relationship between the blue area and the green area? And again, though, I claim there's going to be some sort of a stretching factor. What this function does, this g function, and details to come in a few minutes, but this little piece of area, when it goes through the g function, is going to get stretched out by some factor. And so this blue area is going to be a yet to be determined stretching factor times du dv. Yeah.
And then that's not 3D, right? That just happens to be the shape of g of r.
Yeah. That's right. That's right. This is all strictly two-dimensional. For the moment, we will eventually talk about 3D, but this is all 2D for the moment. Yeah. So bad art. That's right. All right. Anybody else? Okay. So we're basically in business. The big question then is, what is this stretching factor? We got lucky when we were looking at the single variable version of this, and we already had a notion of how to relate input changes to output changes. These aren't changes. These are areas. I can't, right? I've got no sort of convenient foot in the door on that. So that stretching factor formula, I'm going to have to wait to justify what that formula is. For now, just to get the ball rolling, I'm going to throw it out there. I'm just going to write down a formula, ask you to trust me, and we will fill in the blank eventually. And here it is. The stretching factor is the absolute value of the determinant of the derivative matrix of your change of variables function. So for the moment, just take my word for it. Again, we will fill in that argument later. Okay. We're basically ready to get going on an example at this point. A little bit of notation, though. Don't forget the derivative matrix is the matrix of various partials. Right? The output variables with respect to the input variables. Okay. And here's another little bit of notation. Very common. Color choices. Oh gosh, I'll use dark blue. Not the matrix, but the determinant of that matrix is abbreviated like this. partial xy over partial uv. And that's a weird looking notation, and I totally grant that. The less persuasive motivation for this notation is to observe that, literally what this matrix is, it is literally the partials of x and y with respect to u and v, right? It kind of reads, this notation reads like a casual description of that matrix. So that's better than nothing in terms of motivation. Let me give you a better motivation, I think. And that comes from looking at this equation up here, and let's write down the formula for the stretching factor. Keep in mind the stretching, I didn't do that very well. The stretching factor, absolute value, partial xy, partial uv, using this new weird notation. That apparently is what you multiply by du dv. Now, using this notation as I have there, notice there is this temptation to kind of do a cancellation there. And you can probably guess what I'm going to say about this. That's not really true. You can't really do that. That's not legal. This is all garbage. But the temptation's pretty strong, and in a way, this kind of works in some sense, because look what's left over. What's left over is kind of what you might call dx dy. Again, don't hold me to this. This is all garbage anyway, right? But if you write out this result as dx dy, notice that's what dA kind of represents. If I can get this to, dA represents a piece of area in the xy plane. If you were to take this original integral and write it as an iterated integral on this shape, that would be dx dy. So I wouldn't say it works exactly, but at least it kind of tracks or something. It's somewhat consistent at least. Anyway, the fact that this kind of sort of works in some sense is I think a really nice motivation for using this notation. Even though this determinant is not a fraction, in a kind of a sort of a way, it kind of behaves like a fraction, and so it makes sense to write it as a shorthand as a fraction. Okay, so common notation, I'm a fan. I think you'll become a fan, if not now, certainly over time. And with that in mind, we're going to dive in and do an example. Here we go. Now, this first example is deliberately manufactured to be an easy starter example. I'm going to give myself some nice conveniences that will not, in general, be the case, but just so that we can kind of get through one just to kind of get one in the win column. I'm going to start with this sort of oddly convenient example. So here we go. In this oddly convenient example, we're going to start off with the unit square and the UV plane given. And then I'm going to imagine furthermore that I am given this change of variables function, right? And my domain for the integral that I'm actually interested in is the image. It's what comes out of that function. So now let me again confess what it is that's unnaturally convenient about this. I'm interested in a weird domain, doing an integral over a weird domain, but I'm just giving myself the change of variables function, and I'm giving myself the pullback domain. That's going to be my domain for my new integral. In general, that will not be the case. You'll have to figure those out on your own, and we'll talk about how to do that, how to craft good strategic choices there. But again, for the moment, free. Okay, that said, we need to compute our stretching factor. We have our formula up here for our stretching factor. Let me get rid of the mess. Oh. Yeah. Okay, there we go. Let's see. Our stretching factor is the absolute value of the Jacobian determinant. So let's start computing that. That's stretching factor. Here's the Jacobian determinant. Don't forget to take the appropriate partials to get your derivative matrix in here. These are the partials of x and y with respect to u and v. Make sure you get it straight which way it goes. It's very easy to accidentally transpose this. Now in this case, it wouldn't have mattered because these numbers are equal. Lucky break, right? Nevertheless, make sure to keep it straight which way it goes. And so our stretching factor, well, our Jacobian determinant, 4uv minus 9. Now, the little detail that we have to worry about is that our stretching factor is actually the absolute value of that. And so we've got to worry about how do we take the absolute value of some expression where at a quick glance it's not immediately clear, am I taking the absolute value of something that's positive? Or am I taking the absolute value of something that's negative? Or worse, is it sometimes positive and sometimes negative? That's the nightmare scenario. So how do you tell? And it turns out this is very convenient, at least in this case, and every case is different. But check this out. I can literally see in my picture here, keep in mind I'm only interested in this expression on that domain there. That's my pullback domain. And notice, u is the horizontal axis, and I can see right here from the picture u is always between 0 and 1. On my pullback domain, again, I'm just looking at those green points. U is always between 0 and 1. And likewise, this V right here, again, well, there's the V axis. And notice V always between 0 and 1. So this expression right here, 4uv minus 9, well, the U is one of these, and the V is one of these. No matter what point I'm talking about in my green domain, this term is always less than 4. Which means that the thing I'm taking the absolute value of is clearly negative. Everywhere in my green pullback domain. And the absolute value of a negative expression is the negative of that negative expression. Everybody good? Okay. All right. Okie dokie. It's all downhill from here. Let me clean up the mess. Let's see here. Here was our original integral. Right, original integral on this unfortunate, the domain that we don't like. By the way, just as a reminder, why don't we like this domain? Corners. Corners everywhere. Whichever way you slice. This is terrible. Right? Nobody wants to deal with that directly. But we've pulled it back now to an integral on our new domain over here, our pullback domain, which was given, our unit square. And all we've got to do is just finish the sort of the plugging in. Now, we've got everything computed. This is now literally plugging in. Notice that x here, first part of my integrand formula, I need to know what x is. And x is our first output coordinate. So x is that right there, which goes there. And then furthermore, now next term happens to be y. Okay, fine. Well, y, the second output coordinate. I missed. Let's try that again. There we go. Second output coordinate is like that. You just plug those in. That's just literally inferring directly from the given change of variables function and recopying as needed. Last little bit, don't forget our stretching factor. We just computed our stretching factor was 9 minus 4uv. Stick that in there and away we go. We're in business, right? We've just turned our original integral defined on this ugly blue domain. We've now done the pullback, and now we've got a convenient little integral it's got some polynomials in it. I mean, okay, fine, there's several terms there, right? But they're just polynomials. They're easy terms. The big point is that our domain is now super easy. Best possible case domain for a double integral, unit square. Couldn't be easier. Constant bounds in the iterated integral. Zeros and ones, world's easiest numbers, right? Can't beat it. Everybody on board? Okay. All right. Okay, so let's talk about how you do this in general. I started off with an unfairly convenient example where the change of variables function was given, the pullback domain was given. In general, how do you figure this out on your own? And I'm just going to point out that there are certain functions that very often can be convenient. So translations and stretches and rotations, very often useful for this kind of thing. Do notice, though, that whatever your g function does, in the pullback, you're kind of undoing that. And so, for example, if you translate by the vector a comma b, pulling back will translate by the negative. Well, let's see. Let me do it like this. By the negative of a comma b. And likewise for the others. Now I'm going to show you an explicit example here, specifically of a rotation and how what you want to do to the domain is going to be sort of the opposite of what your change of variables function is going to be. And then we'll work through all the details. So here we go. Next example. Okay, there we go. Okay, so here's our domain. The domain is this square. That's our domain for our integral. Notice what a terrible domain this is for slicing, right? Whichever way you slice, you're going to hit either that corner or that corner. Well, actually, you're going to hit both corners. Or if you go the other way, you'll hit these two corners. This is a no-win situation. Okay, what I would like to do, if I could, hypothetically, wouldn't it be nice if I could rotate that clockwise? I would love to rotate that square clockwise. The way I'm in effect going to accomplish that is to view this square as being a rotation of this square. Right? So rotating the pullback yellow square counterclockwise, when I pull back, I will effectively be taking my already rotated blue square and unrotating it back clockwise to get the yellow square. Everybody see what I mean there? Okay. So if you want to rotate your thing clockwise, then your change of variables function needs to be a counterclockwise rotation. Okay. All right. So with that in mind, let's see here. There we go. So my change of variables function there is a counterclockwise rotation. And now here's where I'm going to wave my hands at some linear algebra, Math219, I've made reference to this stuff, several times in the past, and it's really important to make sure that you're really good at this kind of thing. In particular, rotations are linear transformations. Linear transformations are represented by matrices. Matrices can be understood as columns, each of which is the image of the corresponding standard basis vector, and then all of that. And then you got to do the geometry on each standard basis vector. So again, this is all linear algebra prereq stuff. If you're shaky or uncomfortable with anything that I have in purple here, come talk to me in office hours. I'll be very happy to walk you through it. I want to make sure everybody is solid with how to take linear transformations and turn them into matrices. This is just an example of that. So again, take a careful look, please. Make sure you're good. If you're not good, come talk to me. Okay. Okay, so there's our linear transformation. Now we got to take the derivative matrix. The derivative matrix is various partials that have to be computed. Make sure you're good with how to take the appropriate partials, how to organize them to make the derivative matrix. Of course, we need to understand the Jacobian determinant. So we got to take the determinant of that derivative matrix. And as it turns out in this case, that Jacobian determinant's 1. All right, now I claim this is what I'm going to call to be expected. Let's see here. Let me draw focus well here. Okay, so this Jacobian determinant, my stretching factor is 1. Why is that to be expected? Keep in mind, all I did is rotate. And if you think about what happens when you rotate, nothing gets bigger, nothing gets small, nothing's being stretched, nothing's being squished. It's just kind of turning. And so you don't expect, just from a geometric point of view, you don't expect there to be any changes in areas. So you could almost think that you could argue geometrically that the stretching factor is 1. And that's a case that could be made there. But in Math219, I want to be clear, you do have to show me the calculation. I do want to see all of this on an exam question or on a homework question. Does that make sense? All right. Okay, so again, it's kind of all over at this point. And let's see here. Here was our original integral. Our original integral was this on this domain here, which we agree is bad. And we've arranged for it to pull back, though, to this much nicer domain. It's a regular square. It's kind of squared off. The bounds are constants, 0 to 2 and 0 to 2. Right? Really easy domain for this pullback integral. And all I got to do is plug in. So stretching factor, as before, just plug in your stretching factor. Let's see here. We've got to plug in for the function itself. Let's see, what do we do with this x here? Keep in mind, x is the first coordinate of the output. So x, being the first output coordinate, is that dot product, which is that. Right? And then let's see, what is this y right here? Well, y is the second coordinate of the output, which means it is this dot product right there, which is that. Yeah?
In all the problems, will the derivative matrix of linear transformation be the same as?
That's a great observation. So let me point out to everybody what she's referring to here. So we had a matrix A that represents the linear transformation. That matrix A had these numbers in it right here. But we computed the derivative matrix. Weirdly, the derivative matrix is the same as the matrix that represents that linear transformation, and that seems kind of wrong somehow, that a function is its own derivative. Right? This used to weird me out too. Let me show you the single variable sort of version of this. I need some space. Okay, let me squeeze it in here. The single variable version goes like this. If I have t of x, this is just a scalar now, just a regular single variable scalar. If t of x is equal to ax, where again, this is just a scalar, it's not a vector, and so this is also just a scalar, right? Notice that the derivative is that same number, right? So it's not that weird when you think about it this way. The number that we use to represent the linear transformation happens to also be the derivative of that transformation. So something morally equivalent to this is happening in the observation that you made, that the matrix is also, even in the matrix case, it's kind of the same. Yes, short answer, yes, that will always be the case. But good to always work it out. Yeah. Okay, and let's see if I can, okay, now why is this not, okay, there we go. Okay. Okay, so is everybody happy with this example? Now again, at a glance, you look at the integral on the right and you think, look at all those ugly terms, that's terrible. Look at the original integral in blue. That was very seemingly convenient looking. Why is this a good thing? The reason this is a good thing is because this integral on the left has 3 chunks because you keep hitting corners. Each one of those has non-constant bounds because they're angled lines. There's a lot of ugly hidden inside of the shape of the domain for that blue integral. This one in green, the ugly is all visible. It's just constants. They're just ugly constants. They're not that bad. And look at these lovely bounds, constants. All win. All good news. Okay, a couple of little points of order that have to get said. We're not going to worry in Math219 about these things, but in order for change of variables to work, the change of variables function does have to be continuously differentiable. I feel that needs to get said, but every change of variables that we're going to write down is going to be continuously differentiable, so no sweat for us. Likewise, every change of variables function must be invertible, and again, every one we're going to use will be. But that said, outside of this course, if you find yourself getting real creative about a change of variables function, just be careful. Make sure that the function you write down is invertible. That does make a difference. Okay, and with that noted, next example, we're going to first make a general observation. Actually, we'll probably run out of time. But so let me end with a general observation. Reminder, we've been thinking about functions like this, where u and v were the inputs, x and y were the outputs, and my stretching factor involved the partials of the outputs with respect to the inputs. That was just our formula. So why is it xy with respect to uv? Is it because of like alphabetical order or something? No, of course not. Is it because we always, left to right or something? No, we just tend to write things that way, but you don't have to. The point is the partials of the outputs with respect to the inputs. And now with that established, let's entertain what would happen if I had a change of variables function going the other way. Forget about the purple. Let's think about this dark blue. What would be the stretching factor for that dark blue function? And, well, it would be the partials of the outputs. Keep in mind, for this dark blue function, the outputs are u and v. Partials of the outputs with respect to the inputs, which are x and y. So, okay, I've got these two functions here, the purple one and the dark blue one. Their stretching factors are different. They're determinants of totally different matrices with totally different entries, right? Hard to just immediately see any relationship between those two determinants. But here's the beautiful observation. If I were to take some little piece of area here, what would happen if I were to, let's see, oh gosh, color choices. I'll do this in yellow. If I were to push it forward, see what that new little image piece of area looked like, and then come on back. And keeping in mind that these functions are invertible. In fact, these are inverses of each other, right? What do I get if I start with this little orange rectangle, and if I go way over there and come right back where I had been? And, well, I get the exact same area. So altogether, grand total, doing both steps, in particular, let's see, doing the purple step followed by the dark blue step, all together, the stretching factor is 1. And if you think about it, what that means is, if you have a product that's equal to 1, that means that the 1 is the reciprocal of the other. Which is weird, because keep in mind, even though these look like fractions, they're not. Right? That's just notation. That's just convenience. right? These are not fractions. These are determinants. And yet, again, here we have a second example of how even though they're not fractions, again, they behave like fractions. And when stuff behaves like a fraction, it's tempting and convenient to write it as a fraction. So if you find yourself, if you find yourself with your function going the wrong way, and you compute the Jacobian determinant of the function going the wrong way, no sweat, you can compute the Jacobian determinant that you actually needed just by taking the reciprocal of the wrong one. And we're going to see an example next time of why that's really, really convenient. So drawing a line right here, y'all have a good weekend. See you on Monday.